So, about just under 5 hours ago, I charged up this 25 farad supercap to 2.2-ish volts, and it's down to just over 1.5 volts, and it's still going. Let me just hit the lights. Like, it's still blinking out the Morse code, even though the LED is barely visible. Like, the LED seems to need about as much power as the microcontroller, which is pretty incredible. I'm really happy about that. So this is still running the super inefficient code with no sleeping and just like burning cycles to do a sleep. Um, yeah, that's really impressive. Um, so I'm expecting to be able to get about an order of magnitude uh, improvement on power consumption for the microcontroller by using some sleeps more carefully. Um, but I think the leakage current through the caps is going to be greater than that of the microcontroller and the LED put together. So my next test is going to be isolating the microcontroller and the LED, charge up the capacitor again, and then just let it decay, let it leak flat, and then I'll log that as well, and then the difference between those will be the the maximum I'll be able to save if I get clever with my code. But I'm using the logging to SD functionality of my multimeter, which I've never used, but it seems to work just fine. Okay, bye bye.
So this is the code that was running in that test. It's pretty yuck, but I'll quickly skim through it. So at the top we've got the sequence. This is just the bytes that are stepped through bit by bit to set or clear the LED. So it's basically a 10 frames per second, one by one monochrome video. And so we just read the first bit, second bit, third bit, and based on whether it's a 0 or a 1, we drive the LED accordingly. And I have some Python code that generates that byte sequence based on a string. So we type in a string and it spits out the bytes at the end. So far so good. So we define this delay function that just spins its wheels. It just has a for loop and it just runs for a long time, looping, 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 looping until it gets to the end and then it bombs out. So this is just wasting time to add a delay in so it doesn't just go zoop and play through the video all in one hit. Um, so then we have setup. We set up some registers to say port B pin 012 is output. Um, and then we have a loop and we just go through the sequence. So we start at 0 and then while the counter is less than the length of the sequence, increment the counter, and then we pull out the bit from those bytes and then we set the LED to on or we set the LED to off and then we sleep for a bit. So this code is all very hacked together, rough and ready. There's a bunch of stuff commented out. I just wanted to get something to test the hardware. Um, and so this code gave us this graph. So we have this blue line here and this red line here. So this is graphing the voltage in the capacitor over time. So on the x-axis here, we've got up to 40,000 seconds. And so the red line is with the microcontroller and LED isolated. So we're just measuring the uh, self-discharge of the supercap and leakage over the Zener. So those two components will just waste power, turn it to heat. Nothing we can do about that without getting better components. But then there's other trade-offs. And the blue line is the voltage over time running that inefficient hack together code. So you'll see that the blue line drops away quicker, so our voltage runs out a little bit faster um, than our voltage when we're not running the microcontroller. So this shows us that the microcontroller is using some power. How about that? Um, if I picked a random point at like 20,000 seconds and ran some calculations and worked out that about 82% of the power was just leaking away. Across the Zener and through the supercap, and the rest was going to running the LED and running the microcontroller. And so based on those numbers, I thought, we're not really going to see that much improvement by making the code more efficient. I mean, this sets the absolute upper limit is this red line because that's what's set by our hardware. No amount of code optimization could put us above that line. So, there's 82% of our power's being wasted anyway, and this way outperformed my expectations, by the way. So we've got a 25 farad capacitor on there, and it ran usefully. You'd still see the LED blinking at 1.5 volts, and that was like 5 hours. So that's amazing. Um, and that was so that was one 25 farad capacitor, and the final design has six 40 farad capacitors. So we were operating off 10% of the design capacity, and we still did 5 hours, which I'm very happy with. But mostly for the academic challenge, I went back and made the code more efficient. So for starters, I improved my sequence generating code so it spits out a header file with the sequence in it just to make things a bit more humane. It's exactly the same message, it's just SS space S for one-to-one comparison. So we include some stuff in the GCC AVR library and then the header file for the sequence and some macros to make things a bit more readable. So same setup, except we have some power saving measures. We disable the analog to digital converter, and we shut down timer 0 and the ADC. So that turns off the ADC, and that physically shuts down the hardware. So these two things will have some effect. I'm not really sure what proportion they are pulling, but those are basically the two peripherals you can shut down with no other impact on the system. So then, as before, we set up pin B2 as an output, and we turn the LED off, and then we enable interrupts. So then we define this sleep function where we set up the watchdog timer. So this tells a separate low-level timer in the microcontroller, we're going to do something right now. I want you to check on us in 120 milliseconds and see if we're okay. And then we set some other flags. That's some deep arcana, not really interesting. And then we go to sleep. So we power down basically everything. We retain the contents of the RAM, but we stop the clock. We stop the main CPU clock and a few other clocks ticking along in the background. So the only timer at this point is the watchdog timer, which is designed to be very power efficient. Then we define this blink function that does the same as that other one, where it steps through the sequence, but it does it once. So it reads the next bit out of the sequence, and then it increases our counter by 1, and it wraps it back around to 0 if we go past the end of the sequence. And then we have this interrupt service routine, which fires when the watchdog timer goes off. So up here in the sleep, we tell the watchdog, hey, we're going to sleep, wake us up in 120 milliseconds. And then when that watchdog timer fires, it calls this function here. It's not really a function, but it's effectively a function. And that disables the sleep. And that's it. So in our main loop, we just blink and then we go to sleep. And then this effectively halts here, and we stop on line 55 until the watchdog timer fires, wakes us up from the sleep, we go back into our loop, and then we do a blink, and then we sleep, and then we loop, bleep, bloop, 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 bleep, bloop. And this is about as efficient as we can get in terms of power. We could put this blink function, we could call that from the interrupt service routine, but it's generally best to keep these as brief as possible. Just for, something else might interrupt it, and that would be bad news bears. So I didn't really think this would have much of an impact. Given that most of our power is leaking away, I wasn't really expecting us to get huge gains from making this change. But boy howdy was I wrong. So this is the graph so the red is as before, just no microcontroller. The blue is version 0.5 of the code. The yellow line is the new code, and it hoves so closely to the microcontroller disconnected line. It's not funny. So this has drastically reduced the power consumption by like a factor of 20. Well, it's reduced the power consumption by 95%. which is pretty sweet. And I don't think I'm going to bother trying to improve it from that point. I'm just going to add more capacitors to give us more storage. If I hook this up to one 18650 cell, it would run for a week, I think. It was my rough back of the envelope numbers. It doesn't feel right. Maybe I'm off by a factor of 1,000. Anyway, so next up is to do some actual maths to work out long-term trends. This was a nice graph I did showing the difference between the passive and active voltage drop. It came out to be a nice straight line. So yeah, big wins for power consumption with some smarter code. I was really expecting that the LED would be the main power drain as compared to the microcontroller, but both of these versions of code were blinking the same LED, the same pattern. Code 1.0 was running on a slightly faster time base. It was blinking at 125 milliseconds rather than 200 milliseconds approximately, but the scaled proportion of time the LED was on is the same between the two. So I might run some more tests with the LED off 100% of the time and on 100% of the time, but I don't know. I think I might have gone as far as I want to go on this tack. Wow, okay, that was 10 minutes. Okay, bye-bye.